This video will be an introduction to some of the basic properties of the Dirichlet distribution. It's named after Dirichlet, one of the great mathematicians of the 1800s. And the Dirichlet distribution is interesting because it's a distribution on probability distributions. So what is it? So we say that, let me use theta for a Dirichlet distributed random variable. We say that theta is distributed according to a Dirichlet, we write as dir sometimes, with parameter alpha. If, so this means that the density function, which I'll use a lowercase p for, of theta is proportional to, well, I'll just write what it's equal to first. So it's equal to 1 over a generalized beta function of alpha times the product as I goes from 1 to m. So let's say that this theta is going to be a m-dimensional vector. This is going to be a distribution over m-dimensional vectors. May as well make it n, just to keep things simple. So it's a distribution over n-dimensional vectors, and the density is this thing. 1 over this generalized beta times the product of theta I to the alpha I minus 1 times the indicator function that theta is in what's called the probability simplex. So I'll just write S. I'll just write S for the probability simplex. And this is this set S. So S here. Well, first let me tell you what alpha is. Alpha, this was the parameters for our distribution, and this is a vector, alpha 1 to alpha n. And each of these alphas is strictly positive. Just some positive real numbers. And this S here, this set S, is the set of all, let's see, what should I use? X, I guess? I don't know if do I want to use, I'll say X. All vectors X in our n here, such that xi is greater or equal to 0, and the sum of the x's is 1. So each of these is just, so this is just the set of PMFs on the numbers 1 to n. Right, these are just the conditions for a probability mass function. It's just some numbers that are non-negative and they sum to 1. So this is called the probability simplex. And so the Dirichlet distribution is a distribution which has the support of this distribution, that is where it's the closure, to be precise, of where it's non-zero, is on the probability simplex. And so I have to define this beta function here, this thing. That is beta of alpha. Well, let me write 1 over. That's a little clearer. 1 over this generalized beta function it uses the gamma functions. So you can think of it as sort of a generalized multinomial coefficient. Sort of an analogy to a multinomial distribution. So it's gamma of alpha 0 over the product of these gamma functions, gamma of alpha I, product of all those, where alpha 0 is, where should I put alpha 0? Alpha 0 will define to just be the sum of all the alphas, I from 1 to n. So that's this alpha 0. So that's the Dirichlet distribution. That's it. It's just this. It's defined by this density function. And it's a distribution over these n-dimensional vectors, real value vectors. So let's look at a little bit of intuition for what this distribution looks like. Let me give you a couple. So first of all, what's this probability simplex thing? So in 3 dimensions at least I can draw it. If this is the first coordinate, the theta 1 coordinate, the theta 2, and the theta 3 coordinates, then the set of all these, the triples theta 1, 2, and 3 that satisfy these conditions are just this triangle. This sort of, it's you could think of the plane cutting through here through these points, where this is 1 and the others are 0, this is 1, the others are 0, and so on, and it's just the subset of that plane in the non-negative orthant here. So that's a probability simplex, and let's look at a little bit of and a couple examples of what a Dirichlet distribution can look like. So let me different color here. So I'm going to take that triangle and lay it down flat. And so the Dirichlet distribution can look, for example, well, one thing it can do is it could just be uniform, it could just be constant. So one thing, it could just be like a constant here. Another thing it can do is it could have like a hump in the middle, sort of like something sort of Gaussian looking, but it's just constrained to this set. It can also, that it could have a hump sort of near one of the corners or located somewhere else in this triangle. So that's supposed to be sort of like that. And it can also do kind of interesting things, like it can spike up at the corners. So if this is that same triangle again, it can also go, like, for example, it could go like this, spike up at that corner, maybe spike at this corner too, and maybe not on this one. So that's supposed to be spiking up there, going up off to infinity. So you can do all kinds of interesting things with this distribution. And oftentimes we use a Dirichlet distribution as a prior distribution on probability on PMFs on a finite set like this. So it's very useful in Bayesian statistics, Bayesian inference. Now let's look at a couple statistics for this distribution. So let's look at the expected value of one of the coordinates. Let's look at the expected value of theta I, where theta is distributed, Dirichlet. And let's write out what this is. This is, well, maybe I'll just write it first. I'll make a couple statements here, and then we'll prove them. So the expectation of this guy is alpha I divided by, well, I can just write it this way. It's alpha I divided by alpha 0. So alpha 0 was the sum of all the alphas. That's just the mean. So it's a very simple thing to remember. You can think of it as just, it's proportional to the ith parameter, because these are all non-negative numbers, and when you divide by the sum, then in fact this is also a probability distribution. It's a PMF. Another statistic of interest here is the mode. The mode of alpha I, which is the maximizer, and that's alpha I minus, or mode of theta I, is alpha I minus 1 divided by the sum of all those. So if we summed over I from 1 to n, we would get alpha 0 minus n. Actually, to be more precise, let me say it this way. That's a little unclear. The mode of this distribution is the vector alpha 1 minus 1 over alpha 0 minus n. Same thing with alpha 2 up to alpha n minus 1 divided by alpha 0 minus n. So in other words, when we take this vector, when we set theta equal to this vector, then the distribution, this density function, is maximized. So this is the maximizer of the distribution, the mode. And this can be proven. You can prove this using a very similar argument to if you look at the video on the maximum likelihood estimate for a PMF on a finite set, then the same argument that was used to prove that can also be used to prove this. It's exactly the same argument, actually. And let me also give you one more statistic here for the distribution. The variance of the ith. Remember, this is a random, theta is a random vector, and so these are statistics for the ith component of that vector, and the variance for the ith component is, let's see, I don't remember it offhand, but it is alpha I times alpha 0 I times alpha 0 minus alpha I divided by alpha 0 squared times alpha 0 plus 1. That's the variance. And let me make a little remark here. Something to get some intuition for what these parameters are doing, these alphas. If you think about taking alpha I, for example, or let's say 1, say I is 1. So if we took 1, alpha 1, and okay, so well, first of all, let's think about this. So first of all, let's think about if all the alphas were equal to 1. Set that every element of this vector is just a 1. Then the exponents here just become zeros, and so this is just a constant. So in fact, it's the uniform. It's a uniform distribution over the probability simplex. So in particular, that would be this case right here, right? We set them all equal to 1, and we get a uniform distribution. Now suppose we set them all equal to 1, except then we're going to play with alpha 1. So what happens if we make alpha 1 big? Let's say we jack up alpha 1 really big. Then, if we look at the expected value of theta 1, that tells us nominally what theta 1 is going to look like. And when alpha 1 is big, so as alpha 1 is getting bigger and bigger, this number is going to 1 because alpha 0 is the sum of all the alphas. So when all the others are constant, this is going to 1. And so this expected value, well, it's not like that. It's going to be a situation, something more like this here. That if this was 1, 2, 3, the mass is aggregating at 1. On the other hand, let's say that we held all the others at 1, and we took alpha 1 to be less than 1. Remember, it has to be positive, but we could make it like a half or something. Then this exponent that would be minus a half in that case, but in particular, whenever it's between 0 and 1, whenever alpha 1 is between 0 and 1, this is a negative number. So we get 1 over, so when alpha, so we would get like 1 over theta to the 1/2 or something. And that means that when theta is going to 0, when theta 1 is going to 0, like for example, that would be sort of like this one, at least this corner of it, then the density is going to infinity. And so by setting these alphas, by setting alpha 1 between 0 and 1, you can get this sort of behavior. This one we would have set, what was this? I said 2, 3. For this type of situation, you would have to set alpha 3 also between 0 and 1. So hopefully that gives you some intuition for how you can get different types of distributions using the Dirichlet distribution.